Okay, several people told me that there was a problem with the audio, so I'm going to try to do this video recording again. This time, hopefully, I will have the audio working properly. So this will probably be a little bit different from before, but I'm doing a Mathematica file to show an example of the of how you could use Mathematica to solve the project. And I'm going to be copying and pasting from another Mathematica file so that the typing will go quicker. First thing that I do, and I recommend everything, is to quit the Mathematica in case you've been running something before. We're going to use vectors to do these things, and so the first thing after you quit is you might want to define your vectors. This is how, and I'll post this up on the, oh, hang on a second. Okay, I'm back. Basically, this is the way that you would specify the I, J, and K unit vectors. So we'll hit enter on that one. The next thing that I would suggest you do is to write the forces and the moments, some of the forces, some of the moments. So for example here, and I'm making this up, this is not your project, this is maybe not even close to your project, but I'm just making something up. So force is my forces that are acting on the arm or whatever your free body diagram is. Hopefully you've drawn a free body. And obviously, you know, I'm leaving out gravity, for example, here, so I only have the pin forces. So clearly, this is not the answer to your project. This is just an example of something that is complicated, similar to yours. Okay, so here's the force, and here's the MOM. I'm saying that's the moment. So you got the force in the X times a moment arm, and so anyway, so you got your I's, your J's, and K's, and whatnot. So we'll execute that. So now I have forces and I have moments. Then what I'm going to do is I'm going to say summation of forces equals mass times acceleration. So I need to find my accelerations. And so here's how I'm going to specify it. So the acceleration, XLG, that's the acceleration of point G. And I'm saying, oh, I think there's an AG in the horizontal direction, in the I, and an AG Y. I think that's going to the right and up, just like I normally do. I don't know what the numbers are. That's why I say they're positive. When I calculate these things, if they're negative, I'm wrong. They go the other direction. ALF is the alpha, the angular acceleration. And so I'm saying it's theta double dot in the K. So I think it's accelerating to the counterclockwise direction. So that's my accelerations. And now I'm going to formulate my equations. Okay, so here's an example of how to do that. So the first one here, this guy, is the summation of forces. And if you notice there's a period there, I, that's how you tell Mathematica to take the X direction of the force. So this is the summation of forces in the X direction. Those are two equal signs because this is an equation. And so the force in the X direction is equal to mass times acceleration of G, also in the X direction. See the dot I. And then the second equation here is the summation of forces in the J equals mass times acceleration. Summation of forces in the K, and obviously this is going to be dumb because there are no forces in the K direction, and there is no acceleration. So that's going to give me the 0 equals 0 on that. You'll see what happens there. And then here's your summation of moments in the K direction, so counterclockwise equals inertia times angular acceleration. And so we'll execute that. And notice this guy right here. That's the third equation. And like I was saying, the forces in the K direction are 0. And the acceleration in the K direction is 0. And it's telling you that, yeah, 0 is equal to 0. That's true. So that really the equations you have that are useful is 1, 2, 3 equations, right? Because the force in the K, it's true, but it doesn't really help you any. Okay. So now if you count the number of unknowns, you have too many unknowns, and you say, well, count the degree of freedom, etc. And what I have is there's got to be a relationship between the acceleration of G and the angular acceleration alpha. Why? Well, because there's 1 degree of freedom. That's why. So these things should be related. How do you relate them? Well, you relate them by using special point equations. Well, either that or ropes, pulleys, something like that. But in this case, they're special point equations. So here we go. The acceleration of P is equal to APX in the I, APY in the J. The R that goes from G to P is RXI, RY, J. So there's your R vector. Omega is theta dot, or theta tick. In your special point equation, acceleration of P, 2 equal signs, equals acceleration of G. So this is acceleration of P equals acceleration of G plus alpha cross R minus omega cross, it's omega cross R, or omega squared. This is how you say omega squared, omega dot omega, omega squared, because it's a vector, so if you dot it, you'll get a square, times R. So that's your special point equation, right? So there you go. Now yours may be different, right? But something very similar. So I'm just giving you an example. And now what I want to do is I want to take this vector equation. So you see this guy is APX, APY, so the X and Y, right? And then here's the, on the right hand side, you got a number, right? So here's your I component, here's your J component, and your K component 0, right? You're kind of expecting that, I guess. And now what I want to do is show you how to extract the so that you can get things that are not a vector. Okay, so here's one of the easiest ways to do it, since I have this equation called the special point equation. So I'm going to pull them off. So here I'm going to say forces in the X are equal to mass times acceleration in the X. Force in the Y equals mass times acceleration in the Y. The moment equation equals I, right? And notice I'm taking out the force in the K. That was dumb. I never should have done it in the first place. I was just wanted to show you what would happen if you used. It's true, right? But no big deal. And then this guy right here is my special point equation, right? So we'll hit enter on this guy. I made a mistake. Hang on a second. Let me pause and get. Oops, I discovered what I did. I forgot to copy this guy over. So let me bring that over. All right, I'm going to put it right in here. But right after I've done the special point equation, then I'm going to define the left-hand side of the special point equation, right? Here's the left-hand side, acceleration of P. Here's the right-hand side, right? So I copied and pasted for this guy. So now here's the left, here's the right. Now my equations that are not vectors anymore. So force in the X equals mass times acceleration in the X. Force in the Y equals mass times acceleration in the Y. Summation of moments in the K is equal to inertia times the angular acceleration in the K. The left-hand side of the special point equation in the X direction equals the right-hand side in the X direction. The left-hand side in the Y is equal to the right-hand side in the Y. There we go. Now let's execute that one. And so now I've got some nice equations. They're not vector equations. They're just regular old equations. Okay. So now what I'm going to try and do is solve these things. If you count how many unknowns, some of you have been saying, well, I've got this theta dot, right? But if you remember in class, I said you never solve these, F equal ma equations for a velocity. You always solve them for the accelerations and the forces, right? So you never solve your F equal ma for velocities. You don't. What you do, if it's a time spanner, you solve for the acceleration and you integrate it to get the velocities and the positions. That's how it's done. So what I'm going to do is I'm going to show you how to do that. And in this case, you have acceleration of P right here, right? AP in the X and AP in the Y. And so if you count those guys, you got too many unknowns. And you go, oh, that's right. The satellite is tied down. And so I know that point P is in permanent contact with the base of the satellite. The base of the permanent contact means that the body of the satellite is tied down, so it's equal to 0. Okay, so what I'm going to do is I'm going to say, oh, I should have known that, and here we go. APX is 0, APY is 0. The semicolon back here, by the way, says, just I don't want you to print it. Just it's APX is 0, but don't show it to me. And then if you notice, what I'm going to do is I'm going to take my equations, right? I've got 5 of them, and I'm going to solve for 5 things. And the 5 things I'm going to solve for is the 2 forces, 2 accelerations of g, and the angular acceleration. Again, notice you're not solving for theta tick. You're only solving for the accelerations. It's a time spanner. I'm going to get the acceleration, and I'm going to integrate it to get the velocities. And I'm going to show you how to do that. Okay, so anyway, we'll hit enter on this guy, and oh my goodness, here we go. That wasn't too bad. Notice this guy right here in the acceleration terms. It consists of a bunch of constants, which you will know eventually, like Ks, Cs, distance, d, mass, Rx, all those things. So those are distances, those are numbers, those are things that I know. And theta. So that's, and then once you know your theta, theta dot, and all that, you can plug them into these formulas, and you'll know your forces. Okay, so I'll show you how to do that in a little bit. In the class, when you're doing it for a test or whatever, I have promised you that the only way that I'm teaching you for the class to do this is to separate variables and integrate it by hand. What I'm going to show you now is the way that it's actually done when you have a more complicated thing like what you see here, because there's no way I can separate those guys off. Okay, so here's what I'm going to do. I am going to copy and paste these guys. So I have, whoops, I got the wrong one. Let me get rid of that. Let me come back over here. Let's see, copy, and I'm going to paste it in right here. So basically, I'm saying the theta double dot is equal to, and then you just copy that right there. So that's how I did this. You just copy and paste it in. All right, so there's your theta double dot. You can do the same thing, and you can say the Fx, the force in the x direction. Let's go get him. He's right up here. You can go copy. I'm going to hit Control C, Control V. The Fy, the force in the y direction, is 1 equal sign, because I'm saying it is equal to this. It's equal to this thing right here. And paste it in. All right, and then I'm going to hit enter on this. So now I have a formula for the theta double dot. I have a formula for the F in the x direction and the force in the y direction. So I've got these formulas. Now what I'm going to do is show you how to solve this differential equation. This guy right here, theta double dot, that's a differential equation, and I'm going to show you a quick way of doing it. We are going to ask Mathematica to solve it numerically. In order to do that, I have to have the numbers for all of the values. So I'm going to make up some numbers, and I'm going to copy and paste it off from what I've used before. Okay, so there we go. And I just pluck these out of the sky. D is equal to 1, mass is 1, Ks is 1, okay, boom, boom, boom. And you can try some different values and make sure that the thing is working. All I'm going to do is substitute these numbers into the theta double dot, the Fx, and the Fy. And here's kind of cryptic, but this is the way Mathematica does it. You got to know how it does it. What this is doing is it's saying take these numbers and put it into the formula for the theta double dot. And again, I take these numbers and substitute them into the force in the x, right? So that's what that means. If you hit enter, then what you'll find is here is the theta double dot. It simplifies down when everything's equal to 1, not a problem. But if the numbers are different, so it comes up different. So what? But it's still a formula. Okay, so far so good. Now that you have numbers in here and there's no variables other than the things that you want to solve for, I want to solve the equation. So here is how you do that. So you know how to do the solve. In this case, if you do a D solve, you're going to do a differential equations solution. If you put an N in front of it, you're doing a differential equation solution numerically. And here's how you do it. What you do is you have a set of equations, so you have a curly brace. You put the equation in here. So theta tick tick t, second derivative of theta, equals the theta double dot. So it's going to take all of this stuff here, and it's going to be theta tick tick t is equal theta plus theta tick. All right, so that's what will happen there. When you solve differential equations, just like when you integrate, you have arbitrary constants. The way you tell Mathematica what your arbitrary constants are is like this. What you're saying here is that theta tick, the angular velocity at time equals 0, is equal, it's an equal 0. And that theta at time equals 0 is equal 90 degrees. Okay, so those are your initial conditions. Maybe for your problem, maybe they're different. I don't know. It's up to you. And then, so those are your equations that you're going to solve. All right. The only difference here is the fact that you have the initial conditions. Otherwise, they looks just like a regular solve. And then you put a comma and you tell Mathematica what you want to solve for. I want to solve for theta. Okay. Now, because it's numerical, you have to tell it from what time to what time. So you put a comma and you say, I want to solve it from time equals 0 until time equals 10 seconds. Okay, so that's how you're going to solve this thing. Now the answer looks a little weird, but basically what this, and I'm going to show you how to handle this. This guy right here is your solution. It's basically just a bunch of numbers, okay? And what I'm going to do is I'm going to show you how to plot that when you get it, okay? So when you solve it, you should end up with something like this, where it says theta, or whatever you happen to be solving for, is, arrow, blah, 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 just like this, okay? So here's how I'm going to solve it, right? Or plot it, rather. So you say plot. You tell it what you want to plot, right? I want to plot theta as a function of time. And then just like you had up here with the numbers where it says substitute the numbers into the theta double dot. Okay, you're doing the same thing. You're saying take ND answer, the answer to the differential equation, right? See that right here? ND answer, that's the answer. So what you're saying is take the answer and put it into theta. This guy right here is a little bit cryptic, I understand. But what I'm doing is I want to get, because sometimes you'll have multiple answers, right? Maybe it's quadratic. You have two answers. One's the plus square root, one's the minus square root. So what you would do is you would say, take the ND answer. I want the first answer. In this case, there's only one answer, right? But I want the first one, and I want you to put that in there. Okay, so if it was a quadratic or something, maybe you want the second one, right? So you'd put a 2 in there. Okay, so anyway, and then you hit enter, and then there's your plot. Okay, now this is probably not what your plot would look like, because I made this stuff up, right? But anyway, so that's how you would plot the answer. If you well, let me pause. Hang on just a second. Okay, back at you here now. What I would like to do is I'd like to find out what the forces are. I think was one of the questions. And so if you look back here, the force in the x direction, if you notice, it's got theta and theta dot, right? I've shown you how to solve for theta right here. So here's your theta. I need to find theta dot. So here's what I'm going to do. I'm going to copy what I did here, and I'm going to paste it in down here, right? But now, I don't want to do exactly this. I want this to be the, let's call it the in numerical differential equation answer. Well, this would be for velocity, so we'll name it something else. I'm solving the same equation as before, right? Same initial conditions as before, but now instead of solving for theta, I want theta tick. So I want the velocity of this guy. And so now we'll hit enter, and it looks very similar to what we had before. This is the angular velocity, so this is the theta dot. Now what I'm going to show you next is how can you take those two answers and put them in, substitute them in to the forces in the x. Now remember, this is a numerical solution, so it's going to look like this thing called an interpolating function and all that, which is going to be ugly looking, right? Because you want a number, I know that. But what we'll do is we'll make a plot of the forces. Okay, so that's where I'm headed now. And so I'm going to pause it for a minute. And I'm going to go over there and grab the thing and paste it in. Okay, so this is what I did before. Now, let me just kind of build it up one piece at a time, right? Ultimately, I'm going to come down here to this guy. So here's what I do. I'm going to say I want the fx, right? Let me hit enter and show you what that is. Oh, that's that little equation where you have theta, theta tick. Okay, got it. Okay, now what I want to do is I want to plug in theta dot. Well, I have a solution for theta dot, and that's called in the numerical differential answer VEL, velocity. So I go like this, right? So I'm going to put the fx, and please substitute in for me the answer for the velocity, right? So I mean, you can see on where it says input 33 what's going to happen. And I want the first answer to this. You know, I mean, there's only one answer, but you know, it's possible there could have been two. And so I'm going to hit enter, and we'll see what it looks like now, right? So what, if you notice, what it did was it took everywhere that it had a theta tick in the fx, and it put in this interpolating function, which is this weird thing, but numerical. But if you notice, there's still a theta in there, right? So I'm just going to go back up here. I'll click back up there, and I say okay, and then also substitute in the answer, which was what I called the answer to the angle, right? And again, I want the first answer, right? And there's only the one. And so now there is no theta, theta tick. It's all these weird interpolating functions. I'd like to give it a name so that I can type it easily. So I'm going to call this the final f in the x direction, right? Okay, set it equal to this. So bam, there it is, final fx. All right, so that's, if you notice, that's what I did here when I had it paused. I wanted to make sure I was doing it right. Okay, so I've got that guy. I'm just going to get rid of him. Okay, there's the final fx. Now you want to plot it, see what it looks like. Okay, well, the way you plot it is you say plot the final fx from time equals 0 to 10. And kabam, and there you go. Now again, yours is not going to look like this because now, you know, if you notice, mine has the force going up to 10 to the 11. Give me a break. Well, yeah, I made up the equation, so no telling what I'm solving. But yours will not, should not do that. It should be reasonable. You should, you know, you probably have a good feel for, you know, the fact that what is the maximum force going to be, and where should it occur, so you can do that. Now, you can also do the same thing for Fy. So you have a final Fy, which would be very similar to what I'm doing here. And then you can find the magnitude, right? So, you know, you could say I want the square root of the final Fx and squared plus the final, I haven't defined that, so you'd want to do that, final Fy squared, and you're taking the square root and call that the F magnitude, right, something like that. And you could plot that if you wanted to, and now you're looking for the maximum force. Once you have a plot, you can determine magnitude by just reading off of the plot. If you want to get fancy with your plots, to be able to plot them over a smaller range, so for example, this plot down here, it's hard to see what's happening between 0 and 6 seconds because of this big magnitude here. So, you know, you could do things like this and, you know, plot it to 6. Well, I guess it's not helping me too much, but so you can change this and you can get help from the, oh, there we go, that one's not too bad. So in 1 second, it's already up to, you know, 16, 17, whatever it is. I think in the previous video, which doesn't have a good audio, but it goes into a little bit more detail on some of the things with the plot. Anyway, I'm going to call it quits here, and I'm going to go ahead and upload this, and you can look at either video that you want. Hopefully the audio will be better on this one. Okay,